own research area that I'm particularly interested in. Before I do that, I thought you may be familiar with Lowell Observatory, maybe you're not. I just tell you a little bit about what's going on. There's a lot of things going on here at the moment. This is where I work. It's pretty amazing. It's not the Arizona most people think of. We're at 7,000 feet. So it was snowing yesterday a little bit, actually. This is Lowell. We are located in Flagstaff, Arizona, in the northern part of Arizona. So if you've not been here, please come visit. We're be delighted to have you. We're here because of Percival Lowell, of course. Percival, or Uncle Percy as he's called here, was convinced that there was life on Mars, as you know, and he built this observatory to map the canals of Mars primarily. He thought that there was a dying Martian civilization and the canals are their way of bringing water to the arid regions. And that's why he built this observatory in 1895, 1896. He was one of the great science educators or public outreach people of his time. He was sort of like, the Carl Sagan or the Neil deGrasse Tyson of his time. And as I said, he was just convinced that there was life on Mars. It turned out not to be right, at least not the kind of life he imagined. But that's why this observatory exists. So he built this telescope. It's the Clark 24-inch telescope. You can visit, you can look through the telescope today. It celebrated its 125th anniversary last year. And they refurbished it. It's a beautiful telescope. It's so pretty. And the inside is, it's a beautiful wooden dome. It's just pretty amazing. So, so there's a picture of Percival Lowell looking through the telescope, mapping the canals of Mars, that sort of thing. And you can look through the telescope today. It's open every night that it's clear. So Lowell Observatory is best known for the discovery of Pluto, right? Clyde Tombaugh came out here and he discovered Pluto in 1930. And that's our biggest claim to fame, right? It brings a lot of people here to visit us. At the moment, we get 100,000 visitors a year, not including the pandemic times. But we're building a new center that I'll talk about in a moment that we hope will get 200,000 visitors a year. This is a telescope where Clyde Tombaugh took the plates that Pluto was discovered on. You can still visit it. You can tour it today. It's a pretty amazing piece of history. But there are other things that the observatory is known for that are maybe not such common knowledge. For example, Vestos Slipher was an astronomer here at Lowell Observatory, and he really made the first observations that showed that the universe is expanding, even if he didn't realize it at the time. And in fact, Edwin Hubble used Slipher's observations. It showed that galaxies have these redshifts, that they're mostly moving away from us in all directions. And he combined Slipher's data with his to create the Hubble law, this idea that the universe is expanding, basically. But it was Slipher who made the very first observations of this. So it was pretty pioneering work. Vera Rubin also did much of her pioneering work that showed that there's dark matter in galaxies by studying the speeds of rotation of spiral galaxies. And she did a lot of that work out here at Lowell Observatory as well in the 1970s. Today, we have a newish 4.3 meter telescope that's called the Lowell Discovery Telescope. It's located about an hour outside of Flagstaff. And it's a really nice telescope. This is a picture of it at night. Weather's pretty good here in Arizona, of course, so it's able to observe roughly about 300 nights a year. And it's doing everything from comets to cosmology and everything in between, planets, stars, exoplanets, all of that. It cost, I think, $54 million to build. So we have some partners who helped build and buy time on the telescope. So our partners are Boston University, University of Maryland, Yale, Northern Arizona University, and University of Toledo. There's other universities have expressed interest in buying time as well, but that's the current. And Lowell astronomers get about half the time, about 150 nights a year. And there's at the moment about 24 astronomers here at Lowell Observatory. We also have some smaller telescopes, a 31-inch and a 42-inch telescope out about a half hour from Flagstaff, called a region called Anderson Mesa as well. And as I said, we have a really vibrant visitor program. As Steve was asking earlier, we've reopened fully at the moment. We have this open deck observatory for the public that has 6 really amazing and really diverse telescopes that the public can visit. These little blue glow stones are help light the way up to the telescope at night so people can see in the dark. So this is what it looks like. It has a retracting roof. It's got 6 telescopes from a 5-inch refractor. It's got some of the nicest optics I've ever seen, to a 32-inch Dobsonian telescope that you can look through. We've got a plane wave telescope. It's a really, really nice setup for people to come visit. And as I said, we get like, lately we get like 500 visitors a night. It's really hopping. So yeah, all sorts of different telescopes that you can look through. And again, skies are pretty dark here, even in Flagstaff. I can walk my dog at night and we can see the Milky Way, from my house. So skies, we're a dark sky city. So it's a pretty good place. We're building a new astronomy discovery center. We've had so many visitors, we can't accommodate everybody anymore. We get about 100,000 a year, but we're aiming to build this new center opening in 2024 that will allow us to accommodate more than 200,000 visitors a year. Now, I'm heavily involved in developing content for the center and that kind of thing. The basic idea is it's going to tell the story of your atoms from the Big Bang to today and every place they've been. So that's the kind of story that's woven through this center. So we'll have exhibit halls where we'll talk about the solar system, planets, stars, galaxies, the universe. We also have a large theater. It's not a planetarium per se, but it's a large, 180-degree kind of theater that will have both live presentations and, canned ones, animations, that sort of thing, video. We also have a dark sky planetarium. Rather than having an indoor planetarium where you look up at a ceiling, because skies are so clear here in Arizona, we're going to have it on top of our building. And so we're going to use the real sky for our planetarium. The seats have warmers so your bum doesn't freeze during the cold weather. But it's an outdoor planetarium, kind of like if, in Austin, I'm forgetting the name now of the place. Anyway, the outdoor planetarium they have there, it's the same basic idea. We also have something that I think is a bit unique. It's what we call our diverse universe wall. And here the idea is we feature short biographies and profiles of 80 people from around the world and across time who've been involved with astronomy. And the idea is to sort of encourage young people in particular to think about careers in science and to think about becoming astronomers and to show the incredible diversity of people that are involved in astronomy and science. So more than half the people that we feature are women, and we have people from, if I remember right, it's 32 different countries around the world. Just the whole goal is that any child could come in, see somebody on that diverse universe wall and say, that's me, I could do that too, right? And so that's the hope with that. So we hope it will really help to inspire the next generation of astronomers. Okay, so anyway, let me get to the main topic today. But again, if you've not been to Lowell Observatory, or even if you have, please think about coming out here for a visit. It's a pretty exciting place. So as I said, what I want to do today is talk about what the universe looks like on the largest scales. It's one of my own research interests. I'll talk a little bit about that. One of the points I want to make is that astronomers today are like map makers of centuries ago, where you didn't have enough data to make a really accurate map, but you did the best you could. And as you got more data, your map became more and more accurate, right? So this, for example, shows a map of the world in 1570. And if you look at it, you can recognize Africa, you can recognize, India, North America. South America looks pretty sad in this map, right? It's not 100% accurate, but it was the best you could do. Ships were sailing the world, but there was limited data on coastlines and all that kind of thing. In 1664, things were looking much better because more ships had sailed the world, more data had been collected. And so you can see South America now actually starts to resemble South America. North America looks a bit better. Europe, Asia, Africa, Australia, those are not looking bad. And by 1794, that's a pretty good map of the world, right? So it took centuries, but with enough data and enough effort, our map of our planet became clearer and clearer. And so in astronomy, or human beings throughout history have wondered, well, not just the Earth, but where do we exist in this cosmos, whatever it is? What does the cosmos look like? What is this beyond the Earth? And so people have always wondered about this. And the oldest map of the night sky that was created is the Nebra Disc. It was created by, it was found in Germany. It was created by Bronze Age people 4,000 years ago, right? So it depicts the night sky as they saw it. And you can see the clump of stars near the center. That's the Pleiades, for example. And of course, you can see the moon and the sun and all of that. So it's the first depiction of the night sky, the first map of the night sky, if you like, by human beings, at least the first one that's been discovered. So here's another map, a Chinese map from centuries ago, depicting the stars, constellations in the sky. And people have always been mapping constellations in all different cultures, of course. This is a Pawnee star chart from from the 1700s. And again, it depicted the stars as they saw them. So it represents the Big Dipper, the North Star, you can see the Hyades, for example, the Pleiades. So again, humans have always been trying to map the heavens. William Herschel made a scientific attempt to do this by looking at stars in different directions of the sky and mapping or counting how many he could see in different directions. And his idea was that, well, where you see more stars, we could learn about the shape of the universe, essentially, by counting stars in different directions. And when he did that, he found that the universe looks like this, right? This is the distribution of stars that you see in the sky. And what do you know? We're located really near the center of this distribution, right? So that was a map of the universe in 1785. Of course, we know Herschel was wrong too. The reason Herschel was wrong is because he didn't know about all the dust, all the ashes of dead stars that exist throughout space, and prevented him from seeing very far. So there were stars much further than he could actually see because of all this dust and the extinction of light that it causes. So he got the wrong idea, basically, because of this. But we do know from further mapping, and I'll talk about some more in a second, that the Milky Way is a spiral galaxy, and it would probably look a lot like this galaxy if you could see it from far off in space. It's got a bar structure, we believe, at the center, and the sun is located roughly 2/3 of the way out to the edge near a spiral arm. But that's what we think that our Milky Way galaxy would look like today. Here's another Hubble picture of what our galaxy might resemble if you could see it from far off in space again, right? So we think a much clearer picture of what our own galaxy looks like. Gaia, you're probably familiar with the spacecraft, has been busily mapping the Milky Way for the past 5 years. It's going to observe more than 1 billion stars, and it's producing a really accurate 3-dimensional map of the Milky Way, right? So the images you've seen are pretty spectacular, right? So this is the Gaia map, and it's still being improved all the time as more and more data is added. But this is what the Milky Way looks like seen from Gaia. You can see at the bottom right, the large and small Magellanic Clouds, these small galaxies that orbit the Milky Way. You see the plane of the Milky Way and all this dust, all these ashes of dead stars, and the material from which future generations of stars will be built. You see that everywhere. So Gaia is really revolutionizing our 3-dimensional view of our home galaxy. But, while we knew about the Milky Way, we knew about this band of light that goes across the sky, there are also these fuzzy patches of light in the sky called nebulae that nobody really knew what they were, right? So here's a drawing of one from 1847. Just this fuzzy patch of light. Nobody knew were these solar systems being born like ours, or these really far away clumps of stars. Nobody knew for sure. Here's another picture of one from 1849. And of course, it was Edwin Hubble who provided the first proof, if you like, that these were in fact other galaxies like the Milky Way, or distant island universes, as they call them, excuse me, much further from Earth. And he did this by imaging what was known as the Andromeda Nebula at the time. And he was able to detect some stars that varied in brightness. And he knew that there are similar stars in the Milky Way. And so by comparing the brightness of the stars, these variable stars in the Milky Way with those variable stars in the Andromeda Nebula, he was able to show that it was really far away. It was far beyond the edge of our own Milky Way galaxy. And so today, of course, we know that the Andromeda galaxy is our nearest big neighbor and is located about 2 million light years from Earth, or from the Milky Way. In fact, we're on a collision course with Andromeda. In about 4 to 5 billion years, we're destined to collide. So I'll show you an animation of this, actually. Here's a computer simulation showing what it might look like. So this is the Milky Way in a moment, and time is at the bottom right, shows how many billion years from now. In a moment, you'll see the Andromeda galaxy, and also the Triangulum galaxy, M33. But gravity is relentless. So gravity is going to bring the Milky Way and Andromeda closer and closer together. And so, in about 4 billion years, and I encourage you all to come back, it's going to be a pretty amazing sight. Our galaxy is going to collide with Andromeda. And so you watch as they pass through each other, but spraying stars into space, but eventually coming back together to form a single larger galaxy that astronomers have cleverly named Milkomeda. And there you go. That's the future of the Milky Way, right? Again, 5 billion years from now, basically. So we know that there are galaxies everywhere throughout the universe, of course. This is the Hubble Ultra Deep Field. This is kind of flying or zooming into it. So you'll see galaxies moving past you. The Hubble Ultra Deep Field is this incredibly deep image that the Hubble Space Telescope took. It's basically like they left the camera shutter open for 11 days and just recorded light effectively. So you see incredibly faint galaxies. And so in this particular image, which is just a piece of sky, if you look at the bottom left, it's just a piece of sky much smaller than the size of the full moon. And within that region, there are 10,000 galaxies. And so if you extrapolate over the whole sky from that little piece that the Hubble Ultra Deep Field imaged, there must be, oops, sorry. Well, let me go back. Oh, hang on. Sorry, just going back really quick. So within this region, there's about 10,000 galaxies. So if you extrapolate over the whole sky, there are hundreds of billions of galaxies in the universe. And so we can use them to try and map what the universe looks like on the largest scales. Much like Herschel used the distribution of stars to try and figure out what the universe looks like, today we can use galaxies as light sources to map the universe on the biggest scales. If you look at the Earth, for example, if you're an alien and you arrived at Earth and you looked at Earth from a distance, you'd see all these lights everywhere. And of course, these are where the human beings live. And the human beings trace the land on our planet because we don't do very well trying to live in the ocean. So the lights of the human beings tell you about the land and how it's distributed on our planet. And we can do the same thing in astronomy with galaxies and their lights. They trace where the mass is in the universe on the largest scales. So we use them as these markers these luminous markers of how matter is distributed throughout the universe. And so I'll talk about some of the surveys that have been done, but this is a good example, the Sloan Digital Sky Survey. The Sloan Digital Sky Survey has recorded data for over 300 million objects. Most of them are galaxies. And we can actually produce a three-dimensional image. We can measure the distances of these galaxies. We can make a three-dimensional map. And this is a fly-through of what you might see if you could fly through the Sloan Digital Sky Survey. Each of those dots is a galaxy. And as you look now, I'll talk more about this in detail, but as you look now, you can see these different structures. You can see galaxies are not distributed at random. They tend to clump together. And I'll talk more about that, but understanding how galaxies clump together and the biggest structures that they form and what are the shapes of those structures, that actually tells us a lot about the universe and about the conditions in the universe after the Big Bang. And so that's one of the reasons we want to study the large-scale structure of the universe, is to learn more about cosmology, learn more about the conditions in the early universe that gave rise to these kinds of structures. So one of the things we learn by mapping the distribution of galaxies is that they like each other. They're very gregarious. And gravity shepherds galaxies together to form systems of galaxies. It's pretty rare to find an isolated galaxy. So this, for example, is Stephan's quintet. So you see a bunch of galaxies all near each other. Here's another example of 5 galaxies. And gravity never stops, so it brings galaxies together over time. The Milky Way is part of what I would call a cosmic village, known as a local group. Astronomers aren't very clever with their names sometimes. So the 2 biggest members are the Andromeda Galaxy up here and the Milky Way down here, and we're each surrounded by lots of smaller, what are called dwarf galaxies that swarm around us and Andromeda like bees around a hive. And so that's our village. It's about 3 dozen galaxies in total, right? Make up the local group. That's where we live. But there are much bigger collections of galaxies out there. And these are more like the cities of the universe, the urban centers of the universe. So here's a good example. This is the Virgo Cluster, which you can see through, see many of these galaxies through a decent sized telescope in your backyard. The Virgo Cluster is kind of like, the phoenix of the universe. It's a city of galaxies, not the biggest city, but it's a city of galaxies, probably several thousand galaxies. And this one's located about 50 million light years away. So it's actually relatively nearby, right? Then there's bigger, the really metropolises of the universe, like the Coma cluster here. This would be more like the New York or the Tokyo or the Rio de Janeiro of the universe. These are the really big cities of galaxies. And Coma is located about 300 million light years from Earth. There are even bigger systems. This is one called Abell 1689. It's located about 2 billion light years from Earth. And really almost everything, every golden object you see in there is a galaxy in the Abell 1689 cluster. In fact, there's so many galaxies, they really overlap in the center. It's really hard to tell, where one begins and one ends. Just to give you a perspective, there's so many galaxies. Here's another one, Abell 370 is located 4 billion light years away. And if you're wondering what these streaks are, these are gravitational lensed images. So the gravity of such a massive system can bend and distort the light from more distant galaxies it has to pass through, and it creates these beautiful arcs that are called gravitational lenses. So here's an example, again, showing our particular region of the universe, Milky Way, Andromeda. And again, this galaxy is going quite far out, but to put in perspective, you see there's not a lot between us and the Andromeda galaxy. But if you were in one of those big galaxies, like big galaxy clusters like Abell 1689 that I just showed you, or Abell 370, between us and Andromeda, there would be thousands of galaxies in the space between us. They are really densely packed, right? So these are, as I said, the real metropolises of the universe. And we can see these as we look further and further into space, as we look further back in time. So one of the questions I'm interested in, for example, in my research is, if you're an archaeologist, you would love to be able to find the first human settlements. When did human beings first start to gather into villages or communities? And the beauty of astronomy, of course, is we can do that because we can actually look back in time. We can see the past and we can try and figure out, okay, when did the first villages and cities of galaxies first begin to form? So here's an example. This is a city of galaxies, a cluster of galaxies that we see 5 billion light years away from us. And you can see these things existed already then, right? Looking back in the past. Here's one observed with the Hubble Space Telescope, which is a clump of red galaxies here. And we're seeing this looking back 10 billion years into the past. So the universe hadn't been around that long, 4 billion years, and you were already starting to form these cities or villages of galaxies. And of course, we can't see the very faintest ones at such an enormous distance, but we do know that there were these collections of galaxies already many billions of years ago. Now, if you're in a big crowded city, imagine you're trying to walk down the streets of Los Angeles, trying to walk down the streets of New York City. There's a lot of people, you bump into people all the time. And the same thing is true with galaxies. In these dense environments where galaxies are just crammed together, they collide with each other. They tear stars and gas and dust off of each other. And here's a good example. This is two galaxies that have collided. And this one on the right is just tearing the other one apart, basically. It's tearing streams of stars off of that one. Here's another example. So I really love this image. This is really beautiful. So these are actually four galaxies that are just pulling stars off of each other through gravity, like taffy, right? So it's a pretty violent universe. It's a pretty rough universe if you're a galaxy and you find yourself in a really crowded environment. So that's just the way things are. Here's another example, beautiful. These two galaxies are colliding, stream of stars being torn off of this one, just really, really beautiful. I love this image too. This is a spiral galaxy, probably not that different from our Milky Way, seen edge on. And this faint trail that you see around it is the ghostly remains of a galaxy that was torn to pieces by this one. And when it gets torn to pieces, the stars continue. It's like it's like if a jet fighter breaks up in flight, the debris keeps going along the original trajectory for a while at least, right? And the same thing is true with these galaxies. This galaxy was torn apart, but its stars still continue along their original orbits, at least for a while. And so you get this sort of ghostly streaks, the shredded remains of a galaxy that was torn apart by this larger one, presumably. This is an image my colleagues and I took some years ago using the Gemini 8-meter telescope in Chile. And this is a giant galaxy. This is enormous. It's actually, we think, one of the biggest galaxies in the universe. And you could fit dozens of Milky Ways inside of this galaxy, many dozens of galaxies, Milky Ways inside. But in the center, you see the surviving cores of partially digested galaxies. And there's several of them right in the center. And so if you come back in a billion years, they'll probably be gone. Their stars will just become part of this larger system. And we think that's how big galaxies grow, is by cannibalizing their small neighbors. That's one of my areas of research that I do. So here's a computer simulation showing you how bad it gets. This is the birth of a large galaxy. And just watch it for a second and look at all the smaller galaxies that get pulled in by its gravity and torn to pieces, and their stars become part of the bigger galaxy. So it grows to this enormous size over time by cannibalizing its neighbors. So I just let it run for another minute, but it's a pretty frenetic universe, right? So, but this is how big galaxies grow. And we know for a fact that the Milky Way has cannibalized many galaxies during its lifetime. We still see some of the remains today of smaller galaxies that the Milky Way has cannibalized. So what I want to talk about now is how are galaxies distributed on even larger scales. We want to map the universe, again, using galaxies as light sources. So when this work first started, it started many decades ago, but it was a two-dimensional map of the sky, much like the constellations are, right? It shows us roughly where stars are distributed on the sky, but it'd be really nice to produce a three-dimensional map to know what the universe looks like in 3 dimensions. And so beginning in the 1980s, really, there was a lot of pioneering work done, really laborious work to measure not just the positions of galaxies on the sky, but their distance from us to create a 3-dimensional map. This shows some examples. I'll show you many more examples in a minute, but you see again, so sorry, I should mention, so this is the right ascension here, right? And then along this axis is the distance, essentially. It's the velocity, the expansion velocity of the galaxy, which is related to its distance. So each dot here is an individual galaxy. And what you see is galaxies are not distributed at random, clearly, but you also see these noticeable patterns, these large coherent structures in the distribution of galaxies. And so astronomers need to explain, where did these structures come from? When did they form? And what do they tell us about conditions in the early universe that gave rise to these kinds of structures that we see today, right? So that's one of the things I'm really interested in, is how do we map the universe on the largest scales? Here's an example of the distribution of galaxies observed with what's known as a 2-mass survey. It was an infrared survey of the sky. And again, you see these beautiful long plumes, these long filaments of galaxies. And so they seem to be connected together. I'll show you some more examples. And so today we call this the cosmic web. It's like a spider web with all the different threads coming together. We seem to have these kind of threads of galaxies on really large scales. And so this is called the cosmic web today. Some of the pioneering work was done by Janne Nasto and his team. He's an Estonian astronomer in the 1980s. And this shows a plot of what's called the Perseus Pisces supercluster. So every dot in this image is a galaxy. And you see again this enormous structure, this filament. It stretches over 50 degrees across the sky, right? So it's a really big structure of galaxies. Was there enough time for something like this to form since the Big Bang? Clearly the answer is yes, but how, right? And when did these structures begin to form? So we now know that there are these things that we call superclusters. So just as galaxies come together into villages and clusters of galaxies, clusters themselves come together into bigger structures that we call superclusters. Much like if you think about on Earth, cities, combine to form states, states combine to form countries, etc. That's what we see in the universe as well, that even the cities of galaxies, the clusters of galaxies, form these larger clusters that we call superclusters. So here, for example, this is a map showing our local groups. This is where you'd find the Milky Way. But you see, we're on the outskirts of the Virgo cluster. We're actually probably gravitationally attached to it. And there's all these other massive cities of galaxies, the Fornax cluster, Eridanus, et cetera, that are also part of a much larger system of galaxies. We figure this out by carefully and painstakingly mapping positions and distances of individual galaxies. One of the biggest structures that's been discovered so far was discovered just a few years ago. It's called the Saraswati supercluster. It's named after the Hindu goddess of knowledge. And it's home to 100,000 galaxies, it's estimated. So the box here shows a blow up of this supercluster. It spans 650 million light years. It's just enormous, right? And that was discovered from maps of the galaxy distribution. It's located about 4 billion light years away from us, but just an enormous structure. And there's even bigger ones. Several years ago, Brent Tully, an astronomer at the University of Hawaii, after decades of effort, was able to show the existence of an enormous supercluster called Laniakea. Laniakea comes from the Hawaiian word meaning immense heaven. And so it's believed that the Milky Way and the local group are outliers within this supercluster. We're like in the suburbs of this enormous supercluster. It spans 500 million light years from end to end. So again, the local group is located here. You've got Virgo supercluster, but you've got other superclusters, Hydra, et cetera, that all seem to join together into kind of a coherent structure over 500 million light years, right? So just an enormous, enormous structure. Just very recently, back in January, a paper was published claiming to find what might be the largest structure in the universe, or one of the, close to the largest structure. It's cleverly named the Giant Arc, because they said astronomers aren't very clever with their names. It's really, really big. So this shows the positions of where the arc galaxies would appear on the sky. And if you could look at it on the sky, this giant arc will cover more than 20 full moons from end to end. So it's just enormous. And again, it starts to become a question of, could you have formed such enormous systems of galaxies like this since the Big Bang? And what does it say about what's called the cosmological principle? The idea that when you look at the universe on sufficiently large scales, it should look the same everywhere. You know, on smaller scales, gravity brings galaxies together to form systems, but on bigger scales, it should be pretty homogeneous. And really enormous structures like this raise questions about that. Is that really true? Here's an even bigger one. And again, because we're not good with names, it's called the Huge Large Quasar Group. So quasars, as you probably know, they're the really luminous cores of galaxies where there's a supermassive black hole. We think there's supermassive black holes in all galaxies, including the Milky Way. And as material falls into the black hole, some of it is ejected before it falls in as light, these intense beams of light. And they can be seen at enormous distances. They can be seen across the universe. So even if galaxies themselves start to get too faint to see, very, very far away, we can see quasars. They're the brightest galaxies in the universe, essentially. And so a team has been identifying these enormous groups of quasars, they call them large quasar groups, for the past several decades. And then recently they found one that was the biggest one ever discovered. So it's called the Huge Large Quasar Group. It has more than 73 quasars, all near each other in the sky and in distance, excuse me, and it spans a distance of 4 billion light years from end to end. So it's just enormous. It actually raises questions of how could you possibly form something this big? But I should say, when we're looking for structures like this on the largest scale, there is controversy about whether they really are real structures or just some statistical fluke. There have been several papers published that say the methods that these researchers have used to identify large structures are prone to uncertainties, they're prone to systematic biases, and they may identify groups of quasars that don't really exist in reality. Much like when you look at the constellations, right? You see this group of stars, but they're all not actually physically associated with each other in many cases, asterisms and that kind of thing. So are these bona fide systems of quasars in 3 dimensions, or is it just a fluke because of the statistical methods that they use to identify them? So that's a big question mark at the moment. So take all this with a little bit of grain of salt. One of my own areas of research is trying to map filaments on large scales using galaxy clusters and individual galaxies too. And when you look at something like this is the Perseus Pisces supercluster again. And I'm going to circle all of the cities of galaxies, all the densest regions, these clusters and groups of galaxies. And if you look close, you see that the galaxy clusters are quite elongated. And they're elongated in the direction that traces the filament, right? So look at this galaxy cluster here, Abell 262. It's oriented, it's aligned with the filament that it resides in. And this was pointed out, 40 years ago by Jan Anasto and his team, that he said the orientations of clusters and superclusters is a conspicuous property of the superclusters. Oops. And so one of my areas of research is, if you took this Perseus Pisces supercluster and you moved it far away, most of the galaxies start to fade. And all you would be able to see are the densest regions in the center. You could still see those far away. So what I'm doing now, and been doing for years, is trying to use the orientations of faraway galaxy clusters to see if we can trace filaments. Even if we can't see all the galaxies, can we still trace the filaments by looking at these kinds of alignments? These two clusters point towards each other, for example, and these two kind of point towards each other. Can we use this as a way to map superclusters and filaments in the cosmic web in the very distant universe, and therefore the very early universe? And the reason this happens is because we know from computer simulations, and I'll show you a picture, I'll show you an animation in a second, that galaxies flow along these filaments. And where filaments interconnect, the galaxies pile up. And that's how you create these enormous cities of galaxies, these clusters of galaxies. And it imprints preferred orientations on them. And so we can use that to map it. So by looking at the orientations of individual galaxy clusters, we can try to trace filamentary structure at the very earliest epochs in the universe's history. And so that's what I'm trying to do now with some collaborators in Finland and in Estonia and Spain and elsewhere. So as I said, computer simulations show that this kind of filamentary network, or these kinds of the cosmic web, is not a surprise. It's exactly what we expect in an expanding universe with gravity and little lumps, little random fluctuations, even quantum fluctuations in the distribution of matter after the Big Bang get amplified by gravity over billions of years to produce this kind of network of filamentary structures on very large scales. It's no surprise. And I'll show you an example. This is called the Lustrous Simulation. This is a 3D, it's a rotating sphere. And as you watch, this is evolving over time. You watch as the matter starts to flow, and it creates this network of filaments. And you see galaxies and galaxy clusters start to build up in these regions where you've got where you've got filaments coming together, right? So it all piles up there and you get these cities of galaxies. So it's not a surprise at all. And it just comes about, as I said, from an expanding universe, sprinkle some matter in, and wait 14 billion years, that's what you get, right? So I just want to finish up by showing you, nature loves to repeat certain patterns for whatever reasons. And so I've been talking about the cosmic web. I've been talking about these filaments. So here's an image showing nerve cells in a human brain and how they're distributed. And you see, it looks pretty filamentary, right? Here's on the left, the image I just showed is a computer simulation of the cosmic web. So you see the cities of galaxies, you see these long filaments that are interconnected. And there's a pretty uncanny resemblance to the way cells are distributed in our brains. And it's not just that. This is the city of Liège in Belgium, seen from the International Space Station. So it's all lit up, right? We're using the lights of the human beings again to tell us how people are distributed throughout the city of Liège. And again, I don't know, kind of an uncanny resemblance to the sort of filamentary network or cosmic web that we see in the distribution of galaxies on the very largest scales in the universe. Even slime mold. So slime mold are single-celled eukaryotes that form communities, and they send out these tendrils to find food. And here's a computer simulation showing how these slime molds grow over time. And you see again, it's this kind of cool network of interconnected filamentary type structures, right? That these small, microbial colonies create. And there's actually a paper published, I think 2 years ago, that actually used the models for slime mold and how they develop over time to also model how the large-scale structure of the universe, the distribution of galaxies, has evolved over time. So that, yeah, they published this paper in 2020. So pretty cool. You can use models and simulations of the growth of colonies of microbes to also describe the growth of the distribution of galaxies in the universe over billions of years. So again, it's just cool. It's just a weird artifact, but it's pretty cool that nature seems to reuse a lot of these same preferred forms, if you like. So let me finish up. Just tell you what I hope the highlights that you've gotten. First is we can use galaxies to map the universe on the very largest scales. It tells us how the matter is distributed throughout the universe, just like the lights on Earth tell us how people are distributed throughout our planet, right? We see that there are these enormous systems of galaxies that we call superclusters, and they can span millions, maybe even billions of light years. As I said, the largest structures are maybe a little bit controversial. It's not resolved yet. And then when we look and map the distribution of galaxies on these largest scales, we see that the sort of preferred shape, the preferred structure of these systems are filamentary. They're these long threads of galaxies that connect together to create something that we call the cosmic web. So thank you. This is one of my pictures I took in Finland of the Northern Lights. Thank you very much, everybody, for your attention. I'm happy to answer any questions. And if you have questions afterwards too, my email address is there. Don't hesitate to email me. I'm happy to answer anything. So thanks very much.
Dr. Michael West, thank you very much. That was really a remarkable presentation.
Thanks, Steve.
And let me open the floor to questions. Anybody, turn on your microphone.
Okay, let me ask one.
Sure.
If we detect this filamentary structure, and maybe it's like cables or currents or some kind of physical effect that is causing this organization, would there be other material like individual hydrogen atoms or anything else that's transported the same way?
Sure, that's a great question. Yeah, the idea is it's all the matter that follows these filaments. There's a search for dark matter at the moment. We don't know what it is, but the dark matter dominates things, and it will also create these filaments. The galaxies are just that rare bit of the dark matter or the matter of the universe that lights up and we can see, but all the matter should follow these similar cosmic web. Yeah,
I see.
But people are still searching for dark matter, right? We believe it exists, but nobody found it yet.
Well, I have a sort of a disrespectful and perhaps a hostile kind of question for you, Michael.
Sure.
And that is that astronomy by simulation seems to be very, very popular these days, and that perhaps there are many, many small galaxies that we can't see, and these simulations are sort of confirming what we do see instead of experimentalists looking for these other fainter galaxies somehow and maybe finding that these filaments don't really exist, that a lot of these smaller galaxies are well distributed with this even distribution across the universe. I mean, I'm disturbed by this astronomy by simulation. A lot of the talks we've heard have used this idea.
Right. And that's a great point, Mike. I mean, I should say I started my career doing simulations of how, depending on the kind of dark matter in the universe, what it would look like today. So I started my life as a theorist, but then I moved into observational astronomy over the years. But so I'll defend the simulators. I think so your point is well taken, but the question is, might the dwarf galaxies be distributed in a completely different way from the bright galaxies that we see trace these filaments? But if you look at nearby systems like the Perseus Pisces supercluster, for example, even the fainter galaxies follow it. So it's not, you can't say the dwarfs definitely trace the filamentary structure, but there's at the moment no evidence that they don't. And most of the computer simulations, like I showed, that's actually modeling the evolution of the dark matter. And then the luminous stuff, whether it's big galaxies or dwarf galaxies, they should all follow the dark matter because the dark matter dominates the gravity of the universe, right? So it'd be hard to get them to have different distributions, I think. And your point about simulations, it's true. You have to be really careful not to overinterpret simulations, for example, because they're very limited as well. And it's really hard to resolve dwarf galaxies in those simulations at the moment. But they do give us hints about, they go hand in hand, right? The observations and the simulations. So you can see these weird structures in the universe on really large scales, but to understand where they came from, well, the simulations say, hey, it's just gravity and a lot of time, it's not a surprise. But I agree, you don't want everything to be driven by, who is it? Was it Russell or Hertzsprung who said once, oh, you don't need to observe the universe. Theorists could have figured it all out about stars without ever seeing the sky. And that's kind of a weird attitude to take, but I do think simulations give us some guidance, But your point's well taken.
Other questions? Howard had a question about the Discovery Telescope.
Sure.
Is the Discovery Telescope now open to the public or open to non-professional astronomers?
It's not, unfortunately. We've talked about that. I'd actually love to see us do that. We don't at the moment. Actually, at the moment, even the astronomers can't, if you go to observe out there, which we couldn't do for the last 2 years, they put you in a separate room because they're being really cautious. So the telescope operator's in one room and you have to go to another room on the other end of the building. It's not open to the public. Personally, I wish it would. Don't tell anybody I said this, but I wish it would. I used to work at ESO, the European Southern Observatory in Chile, and we used to be open out in the Atacama Desert, far from anything. Every Saturday, people could come and they get a tour of the telescopes. I really wish we would do that at the Lowell Discovery Telescope, but we don't at the moment. I should say, one of the things they do for the Lowell staff here is we can actually put an eyepiece in this 4-meter telescope. So occasionally we get to look through it. That's pretty mind-blowing. Some of the nebulae are bright enough, you really see the colors, and it's pretty amazing. But no, so we're not, the short answer, we're not open to the public out there, and it's an hour outside of Flagstaff. But I would personally wish that we were, but maybe someday.
That really must be quite a sight.
Put comments on TripAdvisor. You want to get in to see the telescope.
Wow. Other questions? Mike, you had a question? Mike Burton.
No. I was just chuckling about putting a note on TripAdvisor. Good idea.
I wish I could see inside the Lowell Discovery Telescope.
All right, I got a quick non-astronomy question, but a weather question. The fires, are they affecting you? Are you closed because of the smoke?
That's a good question. We're not at the moment. So the telescope is in a tiny town called Happy Jack, about an hour south of Flagstaff. And the fires at the moment are to the northeast of Flagstaff. So it's far enough away and the smoke's blowing away from the city. It's not a problem. But having said that, every year, every summer, we lose a few nights because we have to shut down because of smoke. There's always forest fires in the area, or there's controlled burns they do to prevent the forest fires from getting out of control. So every summer we lose some nights when we have to shut because the smoke is really bad for the telescope. Of course, it gets on the mirror, and then if it gets wet, it's very acidic. It's not good for the coating. So we do lose time to forest smoke every year, but at the moment it's not affecting us. It's an early start to the forest fires this year, unfortunately.
Other questions? Anybody? Go ahead.
Hold on, I'm typing something in.
Okay.
Oh, well, where'd it go?
Curtis, just blurt it out, Curtis.
Yeah, just spit it out.
Quite a few years ago, I think it was 2011, a group of us Palomar docents, in fact, went up to Lowell Observatory as a group. Were you there, Mike?
No.
I see you nodding. Mike Burton, were you there?
I think I was actually, yes.
anyhow, we got just a fabulous tour, of course, of all the back facilities at the observatory, and we in fact got to look through they were calling it the Discovery Channel telescope, 4.3 meter telescope
Okay.
at Happy Jack,
Yeah, that's right.
and so we in fact got to look through it.
Awesome.
They told us at the time that in fact they did not want to point it at galaxies because they were too bright. That's what they told us. But I would say we got to look at Jupiter and
Cool.
maybe some other planet, I forget. But the object that blew my mind was the planetary nebula NGC 2392, the so-called Eskimo Nebula.
Yeah.
And it looked just like the photographs.
Yeah.
Oftentimes even in big telescopes. And I can tell you that I've looked through the 5 meter telescope at Palomar.
Nice.
A lot of times things don't. The concept of looking through a huge telescope is sometimes better than the reality of actually looking through it.
Absolutely.
That's what I can say about looking through the 200-inch. But the view of NGC 2392 at the Discovery Channel telescope was just absolutely mind-blowing because it looked just like the photographs. You could see color, you could see all the details in the surrounding, that color that's around it. It was just amazing.
Yeah, what they usually do is they'll show a nebula, like I've seen the Cat's Eye Nebula through it, and that's also just beautiful. You can really see the colors. And then they'll show a globular cluster because you can never go wrong with a globular cluster, right? And so seeing it through the eyepiece on the 4 meter telescope, it's pretty amazing. But you're right, people come in, you guys know from like doing public tours, people come in expecting to see Hubble images when they look through the telescope, and it's just not the way it is, unfortunately. So when you do see all that color and all that amazing clarity with an eyepiece through a 4 meter telescope, it's just amazing. You should come back and visit.
Yeah,
We got all these telescopes now. We got a 32-inch Dobbs, and it's really good for stargazing out here.
Well, it sounds to me like it'd be best to wait a year or two so I can visit the new visitor center.
True. Yeah, true. Fair enough. Yeah, we're supposed to open probably mid-2024. But the new telescope and everything is open already, but yeah, not the new visitor center.
Yeah.
Tell me, what's the budget for building that new visitor center? Do you know any?
Yep. Oh yeah, no, I know too well. So at the moment, and it doesn't help that there's, the supply chain issues and the price of concrete's going up and the price of steel is going up and everything. But at the moment, it's budgeted for 43 million.
43 million.
Yeah. And we've raised money. Our fundraising team is pretty amazing. So they've been able to raise funds through donations, and we're trying to get some additional money from the state of Arizona now as kind of, economic stimulus for Northern Arizona to try and do some other things. But the cost has escalated quite a bit just because of all the craziness in the last couple of years, of course. But it's I think the price tag at the moment is like 43 million.
Good grief.
That's the building and the exhibits inside and the theater and everything else.
Mhm.
One time we had an open house at Palomar, and I was sitting next to a guy, his name, I think Andrew Pickles. He
Oh, I know.
presented Andy Bowden. And I asked him if you were hoping that that the grandson of one of our California senators was coming through on this open house and would persuade his grandmother. At that time we had Barbara Boxer and Dianne Feinstein were the senators. I said, are you hoping that one of these grandkids would persuade their grandmother to fund new construction at Palomar? And Andrew said to me, no, he said, I can't wait that long. He said, I need some wealthy person to come through on one of these tours and write me a check right on the spot.
Yeah, it's hard. Our team's been really diligent about trying to raise funds. And I should say Lowell supporters are super generous. It's really nice because people really like this observatory. And I can say this because I've only been here since 2015, but our donors are super generous. We have this, we have a program, our Navajo Hopi program, which actually goes out to the reservations and tries to bring astronomy and culture together. And people are so generous about supporting that. And so it's nice to work at a place that people really seem to value and appreciate. And for us, it's been hard because, like I said, 100,000 visitors, which is kind of our current level, it's just beyond what we can handle at the moment. And you never want to turn anybody away or not give them as good a visit as you would hope. So we're really looking forward to being able to deliver even better than we have in the past. So that's nice. But yeah, people are super generous.
But you're doing something very good by reaching out to the community. There are certain universities in Southern California, who I won't mention the name of, who think that just because they have a very famous name in technology, think that they don't need to promote themselves.
Yeah.
I won't mention it.
Don't mention any names, please.
But you always have to reach out to the community.
I always say, Coca-Cola never stops advertising, right? Even though everybody knows them. So got to remind people.
Other questions? Let me point out, over here. Let me point out Dr. West's most recent book. It is, as I mentioned at the beginning, A Sky Wonderful with Stars, 50 Years of Modern Astronomy on Mauna Kea. And in addition to Dr. West's essays talked about at the beginning, the volume contains a collection, a very impressive collection of photo essays that depict the Mauna Kea landscape, construction of the observatories, and other related subjects. So that's, get it here, it's University of Hawaii Press.
Thanks very much, Steve. Yeah, I used to be a professor at the University of Hawaii, and I go up to Mauna Kea all the time to use the telescopes. And I remember one day I was sitting in the astronomer's residence having dinner, and I watched these tourists come up and try and open the door, but it was locked. And I thought, I bet I'd love to know what goes on behind the scenes. So I wrote a book. And it was a lot of fun. I spent 2 weeks on Mauna Kea, staying at the astronomer's residence and driving up to take pictures. And it was great. I really enjoyed it. And it's beautiful up there. If you ever get a chance to visit Mauna Kea, go for it. It's amazing.
Let me ask a poorly formulated question back to the cosmic web idea. The universe is expanding, and that means the space between the galaxies is expanding by this Hubble flow rate. But on the other hand, the galaxies are traveling along these apparent filamentary paths.
Right.
So does that have implications for the whole notion of expansion and the Hubble constant specifically?
That's a great question. Because you're right. In principle, if the universe were perfectly homogeneous, the galaxy would just expand with the universe.
Yeah.
But within these filaments, they have what we call peculiar velocities. They deviate from the Hubble expansion. And so that makes it difficult, can make it difficult to measure the Hubble constant. And there's still controversy about what the value of the Hubble constant is. There's something right now called the Hubble tension. It's the idea that when you measure the expansion of the universe on local scales, near us, you get a slightly different value of the Hubble constant than you get when you measure it from the cosmic microwave background, the afterglow of the Big Bang, which can also tell you something about the Hubble constant and how fast the universe is expanding, and you don't get the same answers. And so part of it may be this difficulty of these peculiar velocities. The galaxies aren't flowing perfectly with the expansion of the universe. They deviate from it a little bit. But again, the hope is that if you look on sufficiently large scales, even those peculiar velocities become small relative to the expansion velocities. So really big scales, galaxies should be moving so fast that even if they're moving within a filament, it's just a little tiny blip, basically.
Okay. Thank you.
Sure.
Other things. I had a couple of things here. Hang on. Well, let me ask a question that may get me in trouble. This may earn me some. Well, never mind. While you were talking, I noticed something that relates to your discussion of patterns and the way that nature reproduces certain distribution patterns at large scales, the universe,
Right.
at small scales, slime mold, and at all scales in between. I looked at the patterns and the images and the animations, the simulations we showed that modeled the cosmic web. Then I thought back to the beginning of your presentation when you were talking about the history of Lowell Observatory. And it occurred to me that the patterns that characterize the distribution of galaxies across the universe bear at least a superficial resemblance to the patterns that characterize the distribution of canals on the surface of Mars as depicted in Percival Lowell's maps. Has anyone considered the question whether or not, in preparing his maps, Percival Lowell might have been responding in some way to the same fundamental dynamic of nature that, as you have suggested, drives distribution patterns throughout the universe?
That's a great question, Stephen. I love that so much. I'm going to steal it for my next talk.
Yeah.
That's really good.
It's please, it's yours.
But that's a really good point. I mean, you know, humans are great at searching for patterns, right? And again, if there are certain underlying patterns in all different forms of nature, whether it's the canals of Mars or slime mold or galaxies, it may be that we're you know, sort of pre-programmed in a sense to look for certain types of patterns. And maybe that's what Percival Lowell was seeing, right? Because as you say, if you look at his old drawings of the canals of Mars, boy, it sure looks like a cosmic web, right? It's this
It certainly does, yes.
line. So that's a really good point. I'm sorry, I never thought about that. But yeah, you're absolutely right. But to answer your question, as far as I'm aware, nobody's looked at that here, but it would be really interesting. You know, I thought what you were going to say was, you know, the fact that you see these slime molds and other structures all the way up to the various largest ones have this kind of cosmic web or filamentary pattern doesn't mean the universe is fractal, for example. And there's been discussions about that in the past and whether or not it could be fractal or not, but that's kind of, most astronomers I think don't think so, but it's unresolved at the moment. But yeah, that's a really good point. I should plot up, like, you know, some of Percival Lowell's maps of the canals of Mars with like some of the maps of the large scale structure of the universe and see how well you can get them to line up.
Well, yes, you had two slides with maps on. The second slide in particular very much resembled, I think, the kind of patterns that we've been talking about for the cosmic web.
No, that's a great point. It never dawned on me.
Well, I would guess that what happens, what drives these things in the physical universe, maybe also happens in our own cognitive environment. I don't know.
Yeah, I believe that's true. I've actually done a fair bit of reading about, because so one of my areas of research is trying to detect filaments like in a distribution of quasars, for example. I'm working on that. So you have to use different statistical tests. And I've been actually reading a lot about like Gestalt ideas. You know, how do human beings identify patterns in, say, a bunch of points, right? And there are certain things. Actually, I read a really interesting paper a couple of weeks ago too. It was about using sort of Gestalt theory to explain why different cultures see similar constellations, right? What is it that makes a group of stars stand out? It's not just a luminosity or whatever. What is it specifically? And so I think you're right that there are probably certain certain patterns that human beings are particularly adapted, say, to see or to detect. And certainly Percival Lowell, you know, what he was seeing, we don't think was real, but his mind and his eyes working together thought they saw these kinds of patterns for sure. And, you know, with the the large scale distribution of galaxies, we can try and be more quantitative. We use statistical tests and whatever, but there's still, I run these programs in software in astronomy, and you run this really sophisticated software, it does this and that. And at the end, you still look at it, you go, does that look good? And if not, you say, tweak the parameters or something. So, we are pre-programmed to maybe find certain patterns for sure.
I was noticing in one of your slides, I don't remember which one, where you showed some of the filaments. They were also sort of dimmer tracks of galaxies that maybe
Yeah.
if you could see more of the even dimmer
Right.
galaxies around them, that might also look like a filament.
That's right. I think it's probably true. I often say the main filaments are like a river, and you have these smaller filaments that are like tributaries flowing into it. In a sense, they all feed into it in a way. But you're right. I mean, if you think about every galaxy is a point on one of these maps, and the more points that we can add, the sharper our map becomes. And there's certainly far more of these faint galaxies, as you say, Mike, than the bright galaxies. The more of them we can add, the better our image of the universe will become, the clearer it will become.
I always thought that Percival Lowell was seeing the vascular system in his eye,
Well, that's
somehow
right.
reflected by the optics, but that ties into all the things we've been talking about.
Well, that's right. No, that's right. That's the claim. He was actually seeing, the back of his eye, essentially, right? But you're right. He was still looking for a pattern, and whether it was in his eye or on the surface of Mars, this predisposition to find certain patterns in nature.
Yeah.
Is the instrumentation, the quality of the instrumentation advancing fast enough so that we'll be able to see some of these dimmer galaxies within my limited future lifetime?
It's a challenge because you also need to map a large area of the sky to see the large scale structure of the universe. And so, James Webb, for example, James Webb Space Telescope will go really, really faint. It can see loads of these galaxies, but it's a pretty tiny piece of the sky, right? So it would take forever to map everything. The one thing that will be really good is the new the Vera Rubin telescope, the formerly LSST telescope. That's going to produce, terabytes of data every night. And that will be good at mapping the sky to quite faint levels. So that should probably detect more of these faint galaxies, as you say, Mike, and then allow us to see how they're distributed as well. So it's doable. It's this balance between wanting to survey a really big area, but also wanting to go really faint to see the faint ones. That's they're almost opposites sometimes, those demands.
So it's up to us Palomar docents to recruit gazillions of young men and women to become astronomers, to do these kinds of studies.
Exactly.
And go to Caltech, right?
Yeah.
Yep.
That's after they build a super visitor center at Palomar.
Yeah. Oh, $43 million. We need some very rich people to help do that.
Those play a really vital role in training, inspiring the next generation of astronomers. Here at Lowell, if you look at TripAdvisor, so many of the comments about how much they loved our educators. And our educators are volunteers. Often they're students at the nearby university or retired people who want to stay involved in astronomy. And they can really inspire the next generation. They really can. It's really wonderful to see.
Here in Southern California, we call them Palomar docents.
Yeah.
Yeah.
I was in Finland. I went to the big science museum in Helsinki, and they said they used to call them docents and then educators there, and now they call them, I think it was inspirers, which I thought was a great, awkward but a great name.
Mike, don't get any ideas. Let's keep this on the up and up. Okay.
POI.
Right. Yeah, go ahead. Ken?
No, I just said POI. Palomar Observatory docents, Palomar POI inspirers.
I don't think there's enough room on the back of our caps to put that inspirers on. Take off the D, put on inspire.
Yeah, smaller letters.
Smaller letters.
I tell you,
Okay, we're getting carried away with this now. You're kind of going over the Dr. West. Thank you. You've been very generous with your time.
Oh, my pleasure. Thanks so
Wonderful
much.
presentation. Excuse me.
Thanks very much. I really enjoyed it. They were great questions. I enjoyed it a lot.
And we appreciate your help with the Greenway talks.
Sure.
I guess what I'd like to do is begin to wind this meeting down. Let me mention briefly our next time, what we're doing at the next Greenway talk. I've had to alter our normal meeting routine to accommodate our next speaker's schedule.
Okay,
In that sense, the next meeting will be in 3 weeks,
okay,
okay, on May 14th.
okay,
And again, no meeting on May 7th,
okay,
but the Greenway talks will continue on Saturday, May 14th, when Dr. John O'Mara, Chief Scientist at W.M. Keck Observatory, returns with a presentation titled A Night in the Life of Keck Observatory. In this talk, Dr. O'Mara will describe how science gets done at Keck Observatory from proposal to publication. He will also show us how the staff prepares the 2 10-meter Keck telescopes, configures the instruments, and supports the astronomers during their observations. So again, thank you to Dr. Michael West of Lowell Observatory. My thanks as well to everybody who attended. Thank you for coming.
Stephen, can
Yes,
I jump in real quick just on behalf of Mount Wilson? For everybody who needs a fix on the 7th, we're having a lecture up on the mountain with Jennifer Wiseman, who's senior astrophysicist at the NASA Goddard Space Flight Center, and she's going to talk about the Hubble Space Telescope. So we'd love to see everybody up on the mountain at Mount Wilson on May 7th. You can find out more at mountwilson.edu.
May 7th. Fantastic. Thank you very much for that. Everybody got that? Very good. If that's everything, thank you. Thank you, Dr. West. And with that, I'll close the meeting down and we'll see you in 3 weeks. Thank you, everybody. Bye-bye.
Bye-bye.
Thank you so much.
Thank you.